Hello, everybody. Welcome back to another concrete design video. This one's going to be super simple, just another reinforced concrete beam problem and finding the moment resistance for it. This one's just a little bit different because we have a slightly different cross section with some corners cut out at the top. And we're going to see that in the question here. So it's pretty much saying that we have an irregular cross section with 100 mil by 100 mil notches at the corners. And that's in the compression zone. And it wants us to determine, assuming that it's properly reinforced, the factor moment resistance, and it gives us the factors to work with. And in previous videos, we talked about the formulas that we're working with typically for these problems, but we're going to notice that some variables are going to change, such as this A value. We're actually going to be using A bar because now that we have this unique shape in the compression zone, we need to consider a new global centroid for the shape, but we're going to see that in the problem. But for now, we're just going to proceed normally and try and solve for the variables that are unknown so far. So the first one in this moment resistance formula is the D, which is the effective depth, and that's going to be the total height of our cross section minus the distance to the centroid of this area of reinforcement. So we're going to have 700. That's going to be subtracting that 110 at the bottom. And that is going to give us 590 millimeters. And the next thing, obviously, we're going to need AS at some point for both the tensile resistance of the steel and also for this A. And we're going to solve that simply by taking the number of bars, which is 8, and then using the area of a 30M, which is 700 mil squared. And solving for that, you're left with 5,600. Oh, sorry. Just erase that quickly. 5,600 millimeters squared. And then we are once again properly reinforced. So Fs in this case is going to equal to Fy. And that just means that we're using the yield strength of the steel because the steel is going to yield in this problem. We also need to determine what this TR is going to be, which is this section of the MR equation. And that's very simple. We're just plugging in what we already know. So you have the resistance of steel, which is 0.85 to 400 MPa. And then the area of steel that we just solved for. The millimeters cancels out and it leaves us with a Newton value. And this is going to give us a value of 1904. That's 10 to the 3 newtons. Or that's also equivalent to 1904 kilonewtons. Now let's look at CR, which is an important formula for this problem specifically, because we know that this compressive resistance is representing the resultant force that this compression block is going to be producing over this area. And the only difference in this formula is typically it assumes that you have an A times a B value for this block in this formula. But that's not the case anymore because we have an irregular shape. So we actually need to write this slightly differently. We'll notice that this formula is originally written as follows. So we have alpha 1 phi c fc prime A times B. This A times B is now slightly different because we don't have a rectangular perfect block section, right? So we have to actually convert this to a variable for now, and we'll call that the area of the compression block. In order to solve this, we need to do some rearranging. We know that CR is equal to TR, which gives us this formula in the end here, right? So if you write that down, CR is equal to TR, we're going to have something that looks like this. So you have alpha 1 phi c fc prime, and then the AB part, which is now the area of concrete, which is equal to the tensile resistance, or phi s Fy As. Rearranging for this, you can now solve for your area of the compression block, which is just going to be TR on the top, and then this whole section on the bottom, which is alpha 1 phi c Fc prime. And then plugging into this formula, we're going to have the following numbers. We're going to have 1904 times 10 to the 3, and that is in newtons. Then on the bottom, we have 0.8 for this alpha 1. You can go ahead and solve using this equation up top if you want to double check it, but it's equivalent or approximately 0.8. We have 0.65 here for the phi c and the given compressive strength of 30 MPa. And this will be MPa, so Newton millimeter squared. That millimeter is going to come to the top, and AC is going to equal to this number here, which is 122.051 millimeters squared. Now let me clean up this section so we can solve the next part of the problem. Alrighty, so now we have the important variables from our previous solving process. In this part, we need to now look at the compression block and talk about some important characteristics when you have an irregular shape. And one of those important characteristics is that we now have a different location where this CR, or resultant compressive force, is going to be acting in this block. That's because it's not a perfect rectangular shape anymore. So previously, in this formula here, you see that CR is based on A times B, but that's no longer the case because we have these notches taken out, and that area is representing a perfect rectangular section for this compression block. So we actually need to figure out what the equivalent would be when we remove these sections here. So let's take it step by step and let's look at the equivalent for that. And when we do so, we'll be able to solve for this A value here. So let's see what that looks like. So AC is actually equal to A times B, which is typical for most problems. And then we need to subtract those two 100 mil sections that are notched from the top. And then rearranging this formula, we can actually figure out what this A value is, and then do some local global centroid solving in order to figure out where that CR is going to be acting. So let's start plugging in our variables here. We have 12051 millimeters squared on the left side. The B is 600, and that's times A. And then on the notched side, or the notched value that is resulting from this, is going to be 20,000. Now, rearranging this formula, you are going to be looking for the A value. And solving for that, you're going to have something that looks like this. You have the area of concrete on the top. Bringing this over is going to be plus, and then you're dividing all of this by 600. And solving for that, you're left with approximately 237 millimeters. Now let's go ahead and solve for the centroid of this irregular shape here for the compression block. And that's based on formulas that we've used previously, right? So we have that the centroid for any composite is going to be equivalent to each section's area times the distance away from the global axis, or the reference axis that you're solving with, over the area total of the entire composite. So what that looks like for our case is going to be something like this. So we imagine that this is our first section here, just at the cutoff of where those notches are. So we're going to have 400 times 100 for the depth and the width of this section here. And the y value, y1, is simply going to be 100 divided by 2, since it is a rectangular shape. We move on to the second section, which is just this block below. So the area of this block is going to be now this 600 mil length times the depth, subtracting 100. So we already know that this A value is 237. So we know that that is going to be 237 minus 100. And then I am not sure if I'm going to be able to squeeze it in on the right, but the depth of this y, or y2, is going to be 100, and then plus the A value, subtracting 100, and then dividing it by 2 to get to the center of this next rectangular section. So that's going to look something like this. I apologize if it's not on the screen, but it's 237 minus 100, divided by 2. And then all of this is going to be over the total area. So you're just taking this part and bringing it right down to the bottom. Solving for that, you'll be left with a value of approximately 130 millimeters for a bar. And if you look at our diagram here of where the compression block and the CR, or compressive resistance, is, it's a distance of a bar from the top compressive fiber, meaning that we need to take D minus a bar to get that distance between the couple moment. And that's pretty much the gist of these type of problems. So the final formula, you're simply going to be plugging in TR D minus a bar, which is going to look something like this. You have 1904, which we solved for earlier, right up here, times 10 to the 3 for newtons. And then the D, which is solved for, is 590, subtracting that a bar that we got, which is 130. And that is going to give you a value of 876 kilonewtons per meter.